In this video, we will discuss about triangular membrane elements. We will start in this video particularly with the displacement behavior, and in subsequent videos get ahead with setting up the stiffness matrix and the load vector followed by the transformation vector, the transformation matrix for the stiffness matrix of this element. Now, as we've already discovered, membrane elements are two-dimensional elements which are only undergoing deformation in the in the coordinate plane x, y. That means there are only two axes about which there will be a certain displacement occurring in this triangular element. The reason is that there is, first of all, only in-plane loads which are acting on it. That means you will be able to decouple in terms of linear small deformation theory the in-plane and the out-of-plane behavior of this particular plate. So if I have a generic triangular element as you see in the picture, and this is the overall global behavior with x and y as the coordinate axes, then I will be able to describe the displacements at or a certain function. It can be temperature, it can be displacement, depending upon what kind of material, what kind of problem we are dealing with. In this case, I'm only going to concern myself with mechanical problems and therefore only displacements. So the displacements at each of these nodes in the triangular element, which is a simple triangular element, so 3 nodes at the 3 vertices, I will have x and u and v displacement, which will happen at every node. U will be in the direction of x and v will be in the direction of y. Now let's say this is node I, this is node J here, and this is node K here. Then I have UI, VI, UJ, VJ, and UK, VK as the displacements happening in the x and y coordinate axes. Now we know that for all these different nodes, we have to describe a polynomial function that will be describing what kind of behavior these displacements will have at the particular nodes. Now the simplest one that we can assume is a linear displacement behavior, which we have been working with so far, also with all other kinds of elements. So we will continue working with that one, but I will show you examples of higher order polynomials for triangular elements as well a little bit later. So let's say that we have displacements that I will only describe it for u, but the same displacements can also be described for v. So I'll write it down at once, but then I'll work it out only for a particular kind of displacement. So let's say we have displacement ui, which has to be linear, and we know that it's acting in the two planes, in the two dimensions x and y. That means our polynomial will be dependent on two different coordinate axes. That means I can write ui as c1 plus c2 xi plus c3 yi. Now what you can always ask me, what is this xi and yi? So I should also point that out in the figure. So if I have point node I, then its coordinate or its location in terms of coordinates is given as xi, yi. This is xk, yk, and this is xj, yj. And now I can describe for every particular displacement depending on the certain coordinate location that it's at. So I can similarly write uj as c1 plus c2 xj plus c3 yj, and uk can be written as c1 plus c2 xk plus c3 yk. Now you know that I'm writing the same constants for ui, uj, uk because they are in the same axis, so we can use the same shape function from because they are all linear. In the same way, I can also write the functions for v, and in that case I will use different constants because now it's a different dimension of displacement. So I can write this as c4 plus c5 x I plus c6 yi in the same way, I can write Vj as C4 plus C5xj plus C6yj. And finally, Vk is equal to C4 plus C5xk plus C6yk. So that's how I would describe the different polynomials to describe the linear displacement behavior of every node in this entire system. So in general, if I want to write the equations, for u, I can write it as u in general for every point xy is given as c1 plus c2x plus c3y, and v can be written as c4 plus c5x plus c6y. So, and what I've basically done is that I've already introduced all the different nodal points or the locations into these equations here. So I get 6 different equations for 6 different unknowns. So I can solve these together and these together to get relations for C1, C2, C3 as well as for C4, C5, C6 in the form of shape functions with respect to ui, uj, uk in the first block and vi, vj, vk in the second block. Okay. So in the first case, let me just consider these two blocks as A and B. In solving A simultaneously, I can get C1, C2, C3 as the unknowns. Yeah, and if I solve C1, C2, C3, then I will get particular relations that I can also write down. I would like to write this down because it's quite important in terms of what observations we can make from it. Okay, so I can say here that well, there's not enough space here, so I'm going to write it on the next page. The results that I obtained for C1, C2 and C3. So here you can see that C1 is equal to, when I solve it, of course, I'm urging you to solve it yourself. I will get C1 is equal to 1 by 2a times xj yk minus xk yj times ui plus x of k y of I minus x of I y of k times uj plus x of I y of I minus x of j, x of I y of j minus x of j y of I times uk is C1. C2 is equal to 1 by 2a times yj minus yk times ui plus yk times yi times uj plus yi minus yj times uk. And finally, C3 is equal to 1 by 2a times xk minus xj times ui plus xi minus xk times uj plus xj minus xi times uk. So these are the 3 different constants that I was looking for the first block, only when I was solving for ui, uj, uk together. And here you can see that a, I've used 2a as a certain denominator, common denominator in all cases, where a is actually the area of a triangle. So I can write where 2a is equal to xi times yj minus yk plus xj times yk minus yi plus xk times yi minus yj. So this is the relation of 2a, so 2 times the area of the triangle. You can also of course derive it yourself and you'll get the same result. So if I want to, if now I see, I want you to remember, keep this slide separately. It's quite important. We'll come back to it towards the end of the lecture to see what we can observe from it that's a very special. However, moving on, if I have gotten these terms C1, C2, C3, I have to of course go back and substitute it into the relation that I had over here, right here. So I can call this relation 1 and relation 2. So if I want to find out what is u, then I must go back to the next slide, of course, and I can say substituting C1, C2 and C3 into equation 1 and rearranging, as I always say, in a form that I can get u is equal to n times ui ni times plus nj times uj plus nk times uk, something like this, is what I want to achieve. So I can say rearranging, we get something like this. Okay, and this is quite important result for always. And if I put all this together, then I can always find a certain result for ni, nj and nk. Okay, which I can also which I'm going to write down on the next page. But here I want to just show that by simplification I can also write the u is equal to n u. Can also write it like this. Of course, this is only for 3 different boundary conditions or 3 different degrees of freedom, but I can also of course write it for 6 degrees of freedom, which are actually complete in the element. So I can write this as u of the element is equal to n, which would be a certain matrix, times ui vi, uj vj and uk vk. So this is the complete format of the 6 degree of freedom system. And of course we'll write down n in the following slide, so you will also keep following how it will exactly look like. But the idea is the same. So we assumed a certain linear polynomial for the displacement behavior. Then we put it back into together to solve it to get C1, C2, C3. We put that back into the equation 1, which is the generic linear displacement function. And then by rearranging it, we get it in a certain format. So that brings us to what is the definition for n. So where I can write where shape functions ni is equal to 1 by 2 times a alpha I plus beta I x plus delta I y, nj is equal to 1 by 2a alpha j plus beta j x plus delta j y, and nk is equal to 1 by 2a alpha k plus beta k x plus delta k y. Okay, now I always like to write it in a smaller format, and then afterwards I can easily describe each of the terms because it's much easier to write. But you will also see that there is a certain logic in which they have been put together. So we can write alpha I to be equal to xj yk minus xk yj. Alpha j is equal to xk yi minus xi yk. So you will see the resemblance in the previous situation where we put everything together. And alpha k would be equal to xi yj minus xj yi. In the same way, beta I can be written as everything related to y. So yi minus yk, beta j is equal to yk minus yi, and beta k is equal to yi minus yj. And finally, deltas are all to do with x's. So I have xk minus xj, delta j is equal to xi minus xk, and delta k is equal to xj minus xi. And you see there's a logic behind everything. So when I have a y, I have a k and a j here, and in the same way the other ones are included in the equation or in the relation over here. So this is where the description of all the different terms comes in. Okay, and they have all the triangular elements in general will also have very basic properties. So that means if I will sum up the shape functions, yeah, for the u's, so ni plus nj plus nk, again it should always be equal to 1. So all the other characteristics of shape functions are maintained. So if you look at the characteristics of the shape function, then I will have the summation, so ni plus nj plus nk will be equal to 1. Then we will also know that ni will be equal to 1 when at I, and it will be equal to 0 at j and k nodes. And the same way for all the other nodes as well, it will be of similar properties that we have discussed before. Okay, so this is basically the setup of the shape functions for the triangular element with 2 degrees of freedom at every node. I have worked it out up to the point of getting for u. You can also do it for v, and you will see similar relations for v as well.